In this video, I want to show my milestone 3. And first I want to run it. Okay, and when I press different buttons, one is the teddy bear, two teddy bear, three walk to run, four just running, five okay, fight, and six this is shoot. And when arrow up, it moves faster, arrow down moves slower, and back A means backward, and B means backward, and R means reset. Okay, and now I want to show my code. Here I just move everything, the animation called process animation. I called process animation use GPU. So here I just use CPU to get the keyframe and the time, and then pass everything to GPU and got the result. This part is for the verification part. And this one is get a list of born with TQS. And then I use a uh, magic table and calculate the born word. So first I want to show it the first one, the calculated born TQS part. First, when we use the slurp function, if we don't normalize everything, it looks like this. Okay, only half a body can be shown. But the teddy bear, okay, this one, yeah. Someone looked fine, but someone have strange values. And so when I noticed that, I normalized everything. And now, well, a quarter of the body can be shown. I don't know why. So the only thing I can do is to normalize only the source. Yeah, so everything worked good. So if in your computer it has strange values, you can try to normalize one or both, or maybe only target. Okay, normalize one is okay. So different hardware may have different normalization requirements. This is the first thing. And second one is when I calculate the word, I want to show my magic table here. In my magic table, the first column always saves the depth. So when I read this value, I know how far should I go. So this one, because this one is the first column, so here is the first. This one is actually the second column. So, but the depth is 1. But here I just save it as 2. So everything just goes from 1 and to here. And this one is 3, the depth is 3, 1, 2, 3, depth is 3. And I want to show the result here. Here. Okay, this is from the FBX converter. So for the first hips, well, it already have a depth is 2. So I just save it at here. And when I use it, I use the depth as 2, and actually the real depth is 1 and 2. And this one depth 3, 3 goes here. So the max depth is 18, so it just goes here, goes to the end. And when I use the shader, okay, this is max depth. And first, I always calculate what is the real depth in the row and iterate through number 1, column number 1, not 0, to less than the real depth. And when I calculate everything, everything should be based on the rigid. So the first column value, I always save it as a rigid value, and then calculate each word from here, from the first one and the second one and the third one. So it looks like this. And then we can get a result of the words. And in the animation part, so the local private update gets everything just comment out. This one comment out. So because we have already got the bone word, so we just get it. And in the game part, okay, so prototype animation use GPU, and then calculate the word use GPU. This one getting the bone local but saved as TQS, and this one we get the word matrix. And when we call the update, each one I just showed here, when we just get the real word, and for the skin part, yeah, we just pass the word to the shader, skin shader. And okay, this one should be done. And now I want to show the React converter. First thing first, I want to show the when we got a stack, I want to reduce it to drop some unused frames. So I just reduce. It looks like this. Yeah, here, yeah. I use this one as a well. The first frame always have to keep, and also the last frame. Last frame always have to keep. So I iterate from the keep to something called candidate. And this one is used for tests. We calculate this one for test. So here, okay, the first one keep is 0. So candidate is from keep plus 2 till the last one. And we compare if the calculated test is the same as the real value here. If it's the same, just skip, go on, keep going on. If not the same, the the keep is candidate minus 1 and put it to the new frame. And okay, because we always check the candidate from keep plus 2. So if no, the last candidate, the last frame might be dropped. So if the last one in the final list is not the last one in the original list, we just put it there. And okay, when we check if it's the same or not, we just use the first frame, the last frame, and the key time, and then we slurp it. And after we slurp it, we calculate the angle between the some bone with the first bone in each frame. If A and B, well, I set the value as 0.05. If it's 0.005, the dropped frame is too little. Well, maybe only a couple frames can be dropped. But if I set 0.05, it's dropped about half for the run and for the fight and shoot frames can drop about half. And then because this is we can lose some value when you use this reduce. And I did something extra for restructure the whole frame. My original frame is next frame, key time, and a list of bones. But my new frame um, my new frame reduced. Okay, is I just save the firstborn and key time. Probably here. Okay, okay. Next frame key time and firstborn and a list of Q quaternions. And because the firstborn is already saved, okay, probably this one should look fine. Okay. Mm. This is my old structure, stacks and frames. First, next, keyframe, and each frame have 80 bones. And this is my new structure. For each stack, we have a we have pointer to the frame, and each frame has next prev, time, and firstborn. Because the firstborn we have to keep the TQS, and the rest of the bones we just save the quaternion part in list. Okay, here. And because firstborn we have already saved, so we only have to save the rest of them, so 79. And also for the T part of each bone, it's also 79, so we saved it in the after the just behind the stack. So stack have a pointer to frame and also have a pointer to the static vect. The reason we don't save the S because it's always one, so we can just add it in the engine. And the actual code here. They reduced pose. Okay, just everything as I said. Calculate all the numbers, set up all here, set up all the pointers, and output everything to the memory, to a memory buffer. Then copy the memory buffer to the file. And here, this is the human part. I just use a verify. Okay, so here original frame 13 reduced 28. This one original 271 reduced is 149, about half, and this one is also reduced about half, or at least 100 something. And now I want to show the values. Reduce stacks, here the stacks value, and reduce words. Now we will reduce vectors, the transform vector here. And next, okay, these are the reduced frames and the reduced bone pods. Reduced bone pods are only the quaternions. And then when we put it in the engine, everything should just set up all the pointers and everything to the original one. Yeah. And finally, I want to show the size. I want to show the size. And for the human part, because I put everything in the same file, so the file size looks like this. And we have VBO, which words and tries, the hierarchy, just hierarchy table, and the bone pods, original bone pods with all the frames, stacks, and TQS. And this is reduced bone size pods. And this one is for the skin part, the invert pod and the weight index. And the ratio, the whole file before compression versus the reduced part is 3.8, and I reduce about 74% size. Only if I only compare these two parts, the animation part, I reduce about 5 times and about 80%. And for the beer part, it's even more. And the ratio, the whole file reduced about 4 times, so 75%, and only the animation part reduced about 90%. Okay, and this is my milestone 3. Thank you.